again when I do something. You know, it's fine. No pressure. Yeah, we want the sounds to Thank you again. That's bliss feeling. No pressure. No pressure, but that's exactly the situation.
There we are. Okay. So, just to review, the basic framework for the previous lecture was quantum gravity as an effective field theory, or GR as an effective field theory. Namely, for a large black hole, the curvatures are small, the time derivative is small, and so it seems as though we're in a regime where it makes sense to just take the fields, the action with just the terms of few derivatives and study your system, and we got results that are reasonable. So in particular, because general relativity is its interaction is irrelevant, becomes weak at low energy. The quantum fluctuations of the metric are negligible, and so this becomes quantum field theory in curved space-time, where the metric is more or less specified, and we just study, as we did, quantum fields on that background. And the assumptions and the mathematics that went into the calculation of Hawking radiation are essentially identical to those that go into the cosmological fluctuations. Maybe, I don't know if it seemed any fishier to you, but it shouldn't have. And so the result should be robust in both cases. And of course, in the cosmological case, we have this beautiful match between theory and observation, which we don't have yet for Hawking radiation. But today, what I want to do is to push on this, to start to look at this more closely, and to reveal the paradoxes that Hawking first exposed and that have bothered us for 40 years. And these, by the way, don't seem to have any direct analog in the cosmological case. So the first thing I want to do is to go back to the Bekenstein experiment. So we'll draw our black hole. Make it nice and big. And as before, let me I'm going to need it later. Let me draw a space-like slice. And now, as before, we're going to throw in a bunch of quanta. And previously, each quantum we threw in increased the mass of the black hole. And so we got this nice order of magnitude relation between how big the black hole could be and the maximum amount of bits, amount of information, the maximum number of bits it could contain. But we didn't include Hawking radiation. Now we have this other thing going on where the black hole is also losing mass. And in fact, we could choose to do this in such a way. We could choose to feed the black hole at just such a rate so that the energy we throw in is balanced by the energy of this case, we could do this for as long as we want. So now we can imagine a thought experiment in which we throw in, say, n bits, or I guess you should say n qubits. I think actually qubits should be the default, and we should say c bits if we mean classical bits. But anyway, n qubits. And where n can be as large as we want because there's nothing that limits how long we can carry this on. Let's suppose for simplicity each particle that we throw in is spin a half, and we just look at its two spin states. So we have that the dimension of the interior Hilbert space is, well, at least as there's other stuff, but at least as large as 2 to the n with no upper bound on n. On the other hand, we're talking about a black hole which has, again, by design, by some fixed mass that we're holding fixed, therefore some fixed Bekenstein-Hawking entropy, and so eventually this exceeds E to the Bekenstein-Hawking. And so now we have a problem with this notion that the Bekenstein-Hawking entropy, which we sort of derived by a thermodynamic argument, we have a problem with the idea that it has a statistical interpretation because here we can exhibit seemingly more states than it allows us to have. Now, so far this is ugly but not critical. That is, a failure of this interpretation of this entropy is not as bad as a failure of quantum mechanics. But in fact, now by a small elaboration of this, I will turn this into a failure of quantum mechanics. So now let's suppose that each of these particles that we threw in, suppose that we started on the outside with a large number of entangled pairs, Bell pairs. And for each Bell pair, we throw one in and keep one on the outside. So the extra little flag I've added is the particle that stays on the outside. And so what's going to happen after we've thrown in n pairs, so now let me just erase this and start talking about the new thought experiment. Now what's happening is that after we've thrown in n pairs, let's say we began on the outside with a pure state, but now we have entanglement between the inside and the outside. We have so in particular on the outside, the density matrix is mixed because of this entanglement. S out, the entropy. Again, we have n Bell pairs, each of which has two states. So that's n log 2. A number we can make as big as we want. And now let's let the evaporation proceed to completion. So we throw in our n pairs, and then after we've thrown them inside and we've produced this entangled state between the inside and the outside, we let the evaporation proceed to completion. So now I've got to draw a different diagram here, one I haven't drawn yet. So what happens is the singularity comes to an end. Okay. Good. So what I've added to the picture up here is just the Penrose diagram for Minkowski space. This is the origin. This is the origin. This is null infinity. So this is just empty space, and so this is what the causal structure looks like if the evaporation proceeds to completion. And now we have, again, this time slice. And on this time slice, we can do what all the other lectures have been doing, which is divide the system in two and calculate the entanglement entropy outside. And we can do that on this time slice. And we can do that on this time slice. I want to keep it space-like. And of course, okay, so this time slice is still inside the black hole, and it still has this entanglement between the many bits inside and the bits we've held outside. But now after the black hole disappears, the complete description of the space-time that we're left with is just what was on the outside. This is now just Minkowski space with a bunch of outward flying quanta, or rather plus the bits that we held on the outside. And let me sort of draw the continuation of our bits. They're over here somewhere. And again, on this slice, they're in a highly mixed state, and if we evolve forward a little in time, without some kind of very non-local interaction, they must be in the same mixed state. In fact, I've drawn the surface in such a way that the bit with the part with the information on it, with the bits on it, doesn't change at all. I've just used the fact that time is local to move time forward in the interior in this way. So what we seem to have is that the initial configuration is pure, but that the final state is described by a density matrix of some large von Neumann entropy. And if this possibility was noted by Hawking about a year after his original, discovery of the evaporation itself, and since every step in the calculation seemed trustworthy, the assertion is that in quantum gravity, unlike every other instance of quantum mechanics we found so far, we have to consider evolution from pure states into mixed states. So, basically, in ordinary quantum, everything we do, whether it's ordinary quantum mechanics, whether it's quantum field theory, whether it's even string theory up to this point, seems to be governed by the basic framework of quantum mechanics. We could write this let me write this in integrated form as psi final equals S psi initial, or even in a basis, I'll write that as S final n equals S n m, psi in, oops, I don't want the, in the basis I don't want the bras and kets. So psi final n equals S n m psi initial m. But now this kind of evolution doesn't allow that to happen. And so Hawking's proposal is that in quantum gravity, the correct form of evolution is that we have to work essentially with a density matrix. So rho instead of, I'll write it for, so instead of psi n, call it rho n prime, because the density matrix has two indices. And the evolution he was arguing for was that the final density matrix is some linear functional of the initial density matrix, but this is much more general than this. If, in this special case, if this dollar matrix takes a factorized form, then in fact this evolution law is equivalent to this evolution law, and in particular if the initial density matrix has zero entropy, if it's a pure state, then under this condition the final density matrix will have zero entropy as well. But more generally, this kind of evolution would take a density matrix of zero energy to one of positive entropy. It's hard to argue with this. Every step is very simple. It's just using effective field theory within its regime of validity, and so we should just accept this and go home. But of course, it's troublesome. Let me think about what order I wanted to say things in. Sorry. Okay. Any questions before I proceed? No. Good. Yeah. Sorry. Yeah.
Why should I believe that the causal structure is accurately described by the Penrose diagram you draw? That wheelie line at the top is really effective field theory is broken down. I really don't know what's going on.
Good. So actually, it's not as wiggly as I drew. Right, actually, a funny thing about conformal diagrams is that, it's a little hard to interpret. What actually is happening here, right? So what is happening on? What is happening on the outside is that sort of at this point the black hole has gotten very small. It's approaching the Planck sized. And by this point, it has disappeared. What could have happened in between? Whatever could have happened in between, as long as physics is local, it's not going to affect the states of things that are out here at space-like separation. So that's.
It's obvious that the guys at the top left couldn't be in the causal path of the eventual and concentrated.
So later on in the lecture, I'll draw possible ways. Okay, guys, I think actually, later on I'm going to draw possible ways in which quantum gravity might. I think I know where you're getting. Replace the singularity with some extended space, and I'd rather draw those at the end, about midway through the lecture than now. So So let's suppose that. Let's stick with this picture for. I see. I'm sorry, I didn't fully get your question, but I will come back to this. Yeah. Okay. So before I say why we don't want to believe this, let me give another derivation of it that it's a little more economical, and it's kind of you see, we didn't really as I was doing that, I didn't actually say much about the state of the Hawking photons or the information they might carry. But in fact, one doesn't need to set up this thought experiment of throwing entangled pairs in explicitly, because the black hole is doing this for us all the time. It's producing these entangled Hawking pairs. Of which one escapes and one falls in. And so even without this, we would still, in fact, Hawking's original paper didn't have this idea at all. Just the Hawking process itself leads to a state for the Hawking photons on the outside, which is highly entangled with their partners on the inside, and then the slice ends, and you've got pure to mixed. And in this, so in this case, so now I want to go through a nice little argument due to Don Page for this case of a black hole which is just evaporating. So here's, I'm going to draw an entropy as a function of time up to the lifetime of the black hole. Actually, just an aside, not related to this argument, but just let me do a quantitative estimate. It's how long does the black hole live? So the energy of one Hawking quantum is of order the Hawking temperature, which is of order 1 over the Schwarzschild radius, which is of order 1 over gm. And so the number of Hawking quanta is roughly the black hole mass divided by E, which is then gm squared. Or if you're working in fully dimensionless units, it's the number of Hawking quanta is m squared, which, by the way, is the same order as the black hole entropy. That this is basically the area, but it works. It's consistent with the idea that each quantum carries order 1 bits of information. And now the lifetime would be then this number times the average spacing between Hawking quanta. And there's only one real timescale for the black hole, which is the Schwarzschild radius, or the corresponding time. And so it's this number times the Schwarzschild radius, which then becomes g squared m cubed. So I just do this because somebody may casually say the lifetime of the black hole is m cubed. This is what they mean. M cubed in Planck. And so in this picture, this is m cubed. There are actually lots of 2's and pi's here. There are dimensionless numbers like 10 to the minus 10 to the 4, 10 to the 5, which are kind of funny, but don't affect the arguments at all. Okay, so now what I want to draw first of all is I want to draw Hawking's calculation for first what I want to do is so now we have a black hole. Again, forget the bits we threw. We have just a black hole which is evaporating naturally, and I want to take the state on this slice, and I want to, basically work with wave packets so things are more or less localized along it, and then at some point separate it, as we've been discussing, into two systems, and so then talk about this part here will be the early Hawking radiation, where early is a function of what time we do the division at. But and so we want to talk then about the density matrix for the early Hawking photons and the von Neumann entropy for the early Hawking photons. And so let's think about that. Well, it's very simple. So initially there's none. We emit one. It has some entanglement with its partner. And according to the Hawking calculation, each additional Hawking particle we emit carries about the same amount of entanglement with its partner. And so this curve just goes up and up and up in a more or less linear way, except the black hole is getting hotter as you. But essentially, it rises monotonically. And by the way, this is pretty much immune to small fluctuations, small corrections. I mean, the Hawking calculation as I gave it, was just free field theory. If we tried to include, say, the next correction in effective field theory, which would be the, say, interaction due to the exchange of gravitons, it would first of all be down by this small parameter of the Planck length squared over the black hole radius squared, but it also would have no way to build up, basically. Each additional thing you throw in clearly is increasing the entanglement between the inside and the outside. So you robustly follow this curve. So this is what I called S sub E, the entanglement for the radiation. But also, if we assume that the black hole started in a more or less pure state, and I'll explain later why that is, then also this is also equal to the entropy of the remaining black. So at time E we divide the system into those Hawking particles already emitted and the rest yet to be emitted, the rest of the black hole. They're close enough to a pure state that we can say that these are equal at a given time. And okay, good. So this is one curve. Now let me draw another curve for you, which is the Bekenstein-Hawking entropy for the black hole. Good. So I've regulated it simply by taking a basis of wave packets for my free fields. This is this is not sensitive to ultraviolet issues because basically due to thermal, because it's a thermal distribution, the highly energetic modes are not excited. There was a question, sorry. Yeah, it's a good question, and you'd have to, it would take a, right, I know in the discussions of entanglement entropy, people go to great lengths, say, to define things like mutual information, which are ultraviolet safe, and with a little thought, you could do the same here. But this is, since all the quanta that we're interested in have energies of order of the black hole, temperature, it's not an issue. It's not hard to do. There's not an ultraviolet confusion here. There might be an order 1 confusion, but that's not important on the scale of things. Now, these curves cross. I guess I should use capital B for Bekenstein, small b for black. There. So these things cross, and this is kind of interesting. Now, these are two different kinds of entropy. This is worth having a discussion because I believe every other entropy you've seen in these 4 weeks has been a von Neumann entropy, where you assume you have an exact description of your quantum system and you form trace minus trace rho log rho for the density matrix. And this is a von Neumann, these are von Neumann entropies. The Bekenstein-Hawking entropy is a thermodynamic entropy. It's something that appears in relations like dE equals TdS. And those are very different things. The thermodynamic entropy is a coarse-grained version of them. In many cases, they're equal, but it's really a coarse-grained version. That is, now coarse graining sounds like it's kind of ambiguous. What do we mean by coarse graining? I'm not actually sure what a precise definition of, even though I've taught stat mech and thermodynamics and rushed past this point as quickly as I could. I'm not sure how precisely to characterize coarse graining, except to say that basically the thermodynamic entropy is what the von Neumann entropy would be if we considered all states that look macroscopically the same. So roughly speaking, coarse graining is we don't look at the microscopics of our state, and we consider all states that look the same macroscopically, and whatever that von Neumann entropy would be, that is the thermodynamic entropy for our system. Even though in this case, and I'll say more about this again as we go along, these might be very different things. But the problem is once they cross, now it makes sense. It's fine if a fine grain entropy is smaller than a coarse grain entropy, but it doesn't make sense the other way around. You can't somehow increase the number of states you have by coarse graining, and so there's already this observation is due to Page, and it points out that something funny is happening already at the midpoint of the life of the black hole, long before this moment we were talking about a little while ago, where the size of the black hole becomes Planckian, and something else might happen. Good. So what Page conjectured, well, so actually, suppose instead of a black hole, we were burning a piece of coal, piece of paper, we would draw a curve that starts out like this because we'd start emitting photons, and the photons would be entangled with the remaining paper or coal, and it would go up, and it would go up. But in this case, we know that once the paper or coal is all burned, the remaining outgoing photons have to be in a pure state. So we rise, but somehow if we're burning paper or coal, we have to end up back down here. We've got to follow a curve that looks like that. So this is, ordinary burning. And so if the black hole, if there is really a unity in physics so that quantum gravity is not so different from other parts of physics, then in fact it must also be true that for the black hole, the von Neumann entropy of the Hawking radiation has to follow a similar curve. rising. In fact, Page did a nice calculation. What he showed is that if we assume that the black hole plus radiation is in a rather random state, if the dynamics is rather chaotic, you will actually follow the rising curve very precisely until right near the end is a very slight rounding, and then you will follow the Beck-Hawking curve down. So it would actually follow it even more closely than this picture. Okay, so this is what the Hawking calculation says. This is what ordinary physics would do. And see, the real order one discrepancy in what's happening in the second half of the life of the black hole, which order one discrepancy, in particular drives the firewall paradox, but long before that it drives this whole subject. Okay, so now certainly when Hawking made his argument, people who didn't follow it closely but who understood thermodynamics said, hey, no, he must have coarse grained accidentally somewhere. This must be the right answer. He hasn't kept track of everything. Of course, the big difference is that when, say, coal burns, so initially we have some entanglement between the inside and the outside, but whatever's inside can rattle around and eventually escape. With a black hole, there's a horizon. And so this is entangled with this, but there's no way whatever's in here can rattle around and escape. So the real difference, and it's a very challenging difference between black holes and other thermal systems, is black holes have horizons which seem to put you on this curve rather than that one. Okay, so I think the Page curve is used for the curve that rises and falls, and that is what you would have for an ordinary burning system, a curve that rises and falls, right? It might not rise as far as it's conjectured to do for a black hole, but that's not important. What's important is there's an order one discrepancy between the Hawking calculation and what a thermal system should do. Now, Mathur had a nice way of characterizing this discrepancy using the idea of holographic entanglement entropy. Of strong subadditivity. And since all the cool people are using strong subadditivity, I will too. So, if you don't need this board. So, for strong subadditivity, you need three systems. Actually, let me just sort of draw the picture freshly again. Let me separate. So here's the horizon at some time. Here's some just emerging Hawking mode B. Here's its partner behind the horizon, B tilde, and then here's all the earlier Hawking radiation, E. Now, strong subadditivity says that B tilde E plus SB is less than or equal to B tilde, B tilde B. I just want to keep them ordered so I get them straight in my mind, plus SBE. Okay, so we have these three systems. Now, in this case, if the Hawking process, the Hawking process produces BB tilde in a pure state. This is the squeezed state, the Begolyubov transform state that I wrote down for you in the last lecture. So SBB tilde is 0. These are in a pure state. And also, because these are in a pure state, we can drop them. And so this strong subadditivity becomes S sub E plus S sub B is less than or equal to SBE. Actually, ordinary subadditivity gives you the opposite inequality, so we can just make this an equals. And what this is saying is that we're on the rising Hawking curve. That is, each addition, it's saying, as you see, again, S sub E plus S sub B is equal to S sub E, it's saying that each additional mode we emit simply increases the von Neumann entropy of what's on the outside. So this is a more formal way of saying what this curve is. There's a very nice thing about it, though, because in all of the ways that I've cast this paradox so far, I've focused on the state of particles on this entire long thing that we call a nice slice. And historically, this is emphasized, and it might make you think that we could solve the problem if we could sort of somehow find a way to just say that this slice is unphysical. Mathure's argument talks only about quanta on the outside, B and E, and one quantum, B tilde, just on the inside. So Mathure's argument really sharpened the information paradox. It in effect, rules out a bunch of ways one might want to think about it, and really says the problem is sitting right at the horizon, not deep inside. Now, strong subadditivity is hard to prove. I don't know how to prove it, but you really don't need the full machinery of strong subadditivity for this argument. It's simply the statement that if a given Hawking pair is together in a pure state, I'll have to erase this board soon, but if a given Hawking pair is in a pure state, then the wave function has to be a product of the wave function of that pair and everything that went before. And if that's true, there can be no mutual information, no entanglement between this mode and these. And if there's no mutual information between this mode and these, again, that puts you on the Hawking curve. So you don't need the full machinery of strong subadditivity. It's actually pretty clear that if you just focus on that pair that's produced in a pure state, you got to follow this curve. Okay. Let me think about what I want to say next. Okay, question, please. No. This is good. This is a Hawking mode. Thank you. Sorry. So this is a Hawking mode that appears sometime during the life of the black hole, and this is all of the earlier ones. In fact, you only run into the paradox. The discrepancy appears only if we're talking about a mode that emerged after the page time. Before the page time, there's no problem with following the Hawking curve. After the page time, this argument says we continue to follow the Hawking curve when physics requires something different, ordinary physics, and so we're talking about a mode emitted in this time, and E is everything emitted previously. Thank you. Yeah.
So the typical Hawking mode comes out as a wavelength.
Yes. Oh, good. So. So yeah, at the horizon is sort of an order one statement. Actually, well, it's true. Actually, it's not important in this argument, but the typical Hawking mode actually has a wavelength which I think is 8 pi squared times the radius of the black hole. It's pretty darn big. But it doesn't matter because as you follow that back in time, it actually gets arbitrarily, just because of the nature of the horizon, it actually gets arbitrarily close to the horizon. And so as we follow it back in time, this pair, at some point we want to stop following it back because the wavelength is less than the Planck length. But as we follow it back in time, B and B tilde are arbitrarily close to the horizon. Yeah. This is also, well, yeah, this is also what makes the ultimate paradox so sharp. So I really want to get on to ADS-CFT. So this is the argument as a problem, and so what I want to do is to conclude. Well, there's a lot of little things. The first, it's possible that so we don't know what happens when the black hole is Planck-sized. It's possible that the evaporation never ceases, and we're simply left with a tiny non-decaying black hole with an enormous number of internal states, which is still entangled with the outgoing radiation, called a remnant. But because we could have started with an arbitrarily large black hole, this has to have an arbitrarily large number of internal states. So the three classic alternatives are that information is lost in the way that Hawking describes, that information somehow, meaning the dollar matrix. Second possibility is that, in fact, the system manages to follow the page curve in spite of the argument that it doesn't. And then the third is remnants. And so for remnants, we would actually follow this curve way up until the end. And so we badly violate this relation between the Beck-Hawking entropy and the statistical entropy. But that's life. Now, one could go on for 40 years basically arguing about which of these three alternatives is best, never get anywhere. But happily, ADS-CFT came along, and so I want to talk about that. But I want to sort of, one reason for not believing in information loss is it doesn't fit with the unity of physics, unity of thermal behavior. Another is that if the dollar matrix evolution doesn't automatically give you energy conservation. If we have an S matrix, translation invariance tells you that it conserves energy, that it's a delta function in the energy of the initial state and the final state. If we have a dollar matrix, so M here is final, M prime is final conjugated, because it has two indices. N is initial, and N prime is initial conjugated. Here, translation invariance alone gives you one delta function. It tells you that this is proportional to delta of E sub M minus E sub M prime minus E sub N plus E sub N prime. And so this allows processes in which, say, we start with a definite energy, E sub N equals E sub N prime, and N with a definite energy, E sub M equals E sub M prime, but that E sub N, the initial energy, is not equal to the final energy E sub M. So Noether's theorem with dollar matrix evolution doesn't give you energy conservation. And Banks, Peskin, and Susskind argued it's worse than that. That actually generically this kind of evolution will violate energy conservation. Basically, well, good. So you can, again, this is something we'll go back and forth about. And by the way, we're talking about something rather exotic, an evaporating black hole. But one of our principles of effective field theory, as you've heard several times, is anything that can happen must happen. So if this non-Schrödinger evolution is a basic part of quantum gravity, then we would expect that it would infect not just black hole quantization, but our entire effective Lagrangian. And so this is the sort of hardest technical argument challenging this idea, on top of just the general intuition. So this is why maybe we wouldn't like information loss even before ADS-CFT came along. Problem with remnants is you lose the relation between Beck-Hawking entropy and statistical entropy, and also, having small objects with an unboundedly large number of internal states is not what ordinary physical systems do. It seems to lead to infinite pair production, infinite virtual effects. It just seems like a bad thing. But of course, getting the information out requires requires somehow that stuff that's encoded here manage to travel faster than the speed of light to get out there. So we can't win. There's just nothing good that can happen. Question? Well, that assumes you know something about the production rate. Yeah, I think the answer is, yes. There's sharp arguments against everything, right? So yeah. Again, happily, we no longer have to go through these debates because we now have ADS-CFT, but I wanted to answer the question that was asked about, here's my Penrose diagram for the evaporating black hole. And now, what if, and this is quite plausible, quantum gravity, when you get down to the singularity, actually says the geometry doesn't end in a singularity, but it continues, and we fill in this space. And there's models that do this, and I think this was the actual question that was asked. And now everything's fine, because everything is causally connected. Whatever gets inside can escape. But so how does this fit into my three possible classes of ideas? Well, so this is a remnant, because at the time this light ray went by, late in the life of the black hole is already close to Planck sized, and all the Hawking radiation has come out. So at this point we have entanglement between the Hawking radiation and a small object, and the small object very slowly decays over long time periods. It has to be slow because you have very little energy left, and so you can only emit very long wavelength photons. So this picture would be a long-lived remnant. Okay. So it doesn't give you a new possibility. It's one of the existing possibilities. Another way you might try to complete this diagram, and it seems very plausible, especially if you use the strings breaking and joining, is that at the singularity, a disconnected piece of universe breaks off. And this looks like it must be information loss, because there it's going. Although it's been argued first by Coleman in papers that happily you no longer have to read, and various other papers on wormholes, that actually if you imagine summing coherently over the wave function of the baby universe, you end up with you end up with an S matrix. We end up with an S matrix that depends on the wave function of the baby universe. It's a weird thing. Happily, you don't have to think about this, but it actually ends up being a remnant again. So anyway, I don't want to go there happily because I want to go to ADS-CFT. So you can ask questions while I squeegee, because I got a lot of squeegeeing to do. Wait. So wait. The insightful D brains. What do they do to the singularity? Well, anything on the scale of the singularity is going to fall into. I mean, I've given you two on the previous board there. Yeah. So the right picture is rather. I mean, right. If you start thinking about. So if you say, gravity is going to do something funny at Planckian lengths, and you start asking what it might be, that's a very plausible picture to draw. In fact, in the 20 years ago, there are these 1+1 dimensional models of quantum gravity, which are field theory models. The CGHS model is the kind of characteristic one, and they seem to do to space-time what I've drawn there on the right, the filling in the missing quadrant there. And they're perfectly fine as field theories, but again, they're in 1+1 dimensions, and they're where there's no issue of pair production or anything because there's only room for one of them in the whole universe, in effect. Question? Yeah.
So you said I just don't need to worry about QE divergences. Shouldn't I expect there to be some divergence of Neumann Entropy from strawberry
So all I want to say is, regulate this in an arbitrary way. Since the relevant, let me flesh out what I said before. Since the relevant modes have, again, energies of order of the Hawking temperature, regulate this in an arbitrary way with your regulator just a little bit higher than the Hawking temperature. And that will capture all the physics that you want. And the now regulator dependent part will be some will be something of order the Hawking temperature times some fixed number. And that's parametrically small on the scale of the things that we're talking about. There's probably a better, I'm not sure I have ever thought through of the best way to do the separation into early and late. It really comes to, just take a basis of localized modes. Only keep the ones that have some reasonable probability to be thermally excited, and just take that subsystem and divide that subsystem into two parts. That's kind of a regulator already. I've just not included the UV modes in my system. Question?
Are you saying it's really enough to have patches of order in the distortion rate smaller than the distortion rate?
Wait, for what? Sorry.
You were saying that you can have I didn't understand, you can have energy cutoff?
For the purpose of counting entropy, yes, because the higher modes are not excited thermally. Well, remember, the lifetime of the black hole is m cubed. So having a patch of size m is small. We're the whole space that we're dividing in two has a size of order m cubed, the lifetime of the black hole. So I, putting my UV cutoff at just cutting out a chunk of length m in the middle is a small perturbation on what I'm measuring. Okay.
The size of the black hole.
Yeah. It's the size of the. It's really big. Well, it's. If you look at the entire train of Hawking photons outgoing, it's really tiny by comparison. So, yeah. Yeah. By the way, just want to mention, if you look at yourself in time, you're a tiny fraction of a light second in spatial directions, and you're years in the time direction. So you're very asymmetric. You're not really very big, and neither is a black hole. Anyway, question back here. Yes. I'm just using the fact that anything behind the horizon is behind the horizon and can't influence what's on the outside. That really is all that goes into it. Yeah.
Can we think of the black hole as a quantum memory?
Can we think of the black hole as a quantum memory? I'm just going to say yes and go on because I'm sorry. Let's talk about that after the lecture because yeah.
You're setting this entanglement between modes, which are, the important thing is to resolve modes on one side of the horizon. That's really but if you're really saying that we can have a spatial cutoff, which is of order the size of the black hole,
right,
then I don't understand where the support of these modes is.
Let me Yeah. If you take so remember, so you have this. I'll say this one more time. I'm going to have to move on. You have this outgoing train of Hawking photons, and you cut out a black hole-sized gap in that train to separate into two pieces. If you follow that train back towards the horizon, that gap is getting smaller and smaller as it approaches the horizon, just because of this geometry of the way the horizon is a bifurcation surface for light rays. Yeah. I was talking about the Hilbert space, but I can use that since these are to a very high approximation free fields. I can use that separation at different times. Yeah. So ADS CFT. So in the question period yesterday, I got a bit into the ideology of it, but let me run back a little bit again. So actually, I looked at Joel's very nice lectures, and he started, and over much of his lectures, the way he presented it is, suppose that we have a quantum theory of gravity in the bulk. Then we can use that to define a conformal field theory on the boundary. And this is true and very beautiful and pretty much indisputable. But it by itself, it's not enough, and it's not the whole story. Because if that was all it was, then, I mean, I want to use ADS-CFT to define quantum gravity. I want to go the other way. And in particular, if I want to try to draw conclusions about what happens in black holes, well, suppose my weird quantum theory of gravity has remnants or destroys information. It just will define some weird conformal field theory that does the same things. I want to start with a conformal field theory that I know something about, that I know it doesn't do weird things, and then use this. And of course, he did talk about the specific example. Say, for example, the n equals 4, d equals 4 theory. And just to sort of remind you briefly, this is derived, and it's not much of a derivation, by supposing that the interpolation between d branes and black branes commutes with the low energy limit of which gives you on the one side n equals 4, d equals 4 SUN theory, and on the other side 2b in ADS5 cross S5. It's not much of a derivation since we don't really have definitions of what's on top, but it's the kind of thing that actually seems to be, very robust. By the way, so there are a couple of parameters here. So there's obviously n of SUN, and there's lambda, which is the 't Hooft scaling, is G Yang-Mills squared n. And it's just for reference, it's worth remembering what those are on the gravity side. So here we have two-dimensionless parameters. On the gravity side, we have three length scales. We have the ADS radius, the string size, and the Planck length. And so these three these two-dimensionless numbers become two ratios. The ADS size in Planck units to the fourth power is the size of the gauge group, and the ADS size in units of the string scale is lambda. And so in order to have gravity, first of all, be classical, the Planck scale small, and secondly, be effectively a field theory, then we need n and lambda to be large. Now, sometimes people talk about weak versions of the duality, in which maybe the duality is only asymptotic in 1 over n or in 1 over lambda. And if we're only asymptotic, then you could believe some subtle thing like information loss would be, would be hidden in the subasymptotic stuff that you don't see, and you couldn't learn anything about it. Now, in particular, let's say as lambda goes to infinity, so as lambda goes to infinity, what's happening is the strings are going to 0 size. Now, there are a lot of people who work on ADS-CFT at the level of general relativity and never see a string. And so they're really, only using the duality in this rather extreme limit. But there is abundant evidence that, that the duality has the full string theory in it. It has states which have detailed properties of strings. Similarly, over here, you might say, oh, it's just a classical theory of gravity. But the gauge theory, which is something we understand and is well defined, is a full-fledged quantum theory, and so it has unitarity in some sense forces a lot of the finite end structure from the infinite end structure. So these two theories, well, I'm going to take the attitude that this is something I know how to define exactly, And, so other things I know about this theory. We know that this theory has a full set of states that are in one-to-one correspondence with the states of gravitons in AdS5 cross S5. That's because these are supersymmetric states, so we can say this with complete reliability. In fact, we also know the three-point functions from supersymmetry, so we know that these graviton states couple to energy. So whatever this thing is, it certainly looks a lot like a theory of quantum gravity, and it's hard to, and so I'm going to take this as my definition of quantum gravity and ask what does it say about, and this also has states, and I'll describe this in the next 30 or 40 minutes of my talk. It also has states which look very much like black holes. So there's very, very strong evidence that this is it's a theory which is so similar to quantum gravity that it's hard to see how it could be anything else, because again, quantum theories are pretty constrained. So this is the exact thing. And so the argument then is we know how to define this theory a la Wilson. We know that it doesn't destroy energy. It doesn't destroy that we know that it satisfies Schrodinger-like evolution. So the dual gravitational theory as well. Also, remnants would mean we know that quantum field theories don't have spectra with unbounded numbers of states below some given energy. We know enough. This even at strong coupling, I think we know enough about this quantum field theory. In particular, if that happened, the system could never be in thermal equilibrium. And I think we certainly know enough about Yang-Mills even at strong coupling to be pretty confident that it has has states of thermal equilibrium. So this side doesn't lose information or remnants, and so this side doesn't either. That is, we can consider doing the whole thought experiment inside of AdS. It has some translation in the gauge theory, and it must somehow the Hawking radiation must be unitary. So it's not very satisfying because it doesn't tell us how the information gets out, but it tells us that it must. Of course, not everybody wants to believe the assumptions that led to here, but I find these assumptions more trustworthy than any of the. I trust them. So what I want to do with the rest of this section, I guess it will leak into the next, is to flesh out a little bit this argument. There's not much more to flesh out, but I want to describe a little bit about black holes and anti-de Sitter space, and also just about so the dictionary. The dictionary again is that there's a one-to-one mapping of the Hilbert spaces. Every state in the CFT is in one-to-one correspondence with the states in the bulk. And also, there's this dictionary of observables, which Joao used, and I'll repeat the simplest part of it. The limit as we approach the boundary of some bulk operator, some bulk field, appropriately scaled in terms of the dimension operator. This has a good limit, and this limit describes some local thing that lives on the boundary, and that's a conformal field then of the conformal operator dimension delta in the boundary. So this is the base. There's a one-to-one mapping of states, and there's a mapping of observables for which this is sort of the simplest and most useful piece. Okay, so I guess I will also so when I talk about the state space of states, it's worth remembering something. It's kind of an axiom in quantum field theory that you can make any state by acting on the vacuum with local operators. So here I'm acting on the boundary here with these O's. Via the dictionary, this corresponds to acting near the boundary with field operators. So what we're doing in the bulk is we're creating modes going inward. We can excite arbitrary gravitons and so on, strings on the inside, but also we can throw in enough energy that we can be confident that what forms in the center is a black hole. And so the duality sort of implies that that the Hilbert space in the bulk consists of all black holes that we can form, by this kind of generalized sort of collapse. And as I said in the last lecture, all of my black holes are one-sided in this way. I have to be careful not to draw a second ADS space, or else a wormhole might form. Okay. So, also, you might wonder, whether it's enough to think about black holes in anti-de space. I mean, we don't live in anti-de space, but all of the Hawking paradoxes and so on exist in this context as much as they do in flat space. In fact, there's kind of a historic sort of thought experiment that people do in this field where they surround a black hole with mirrors to direct the radiation back in and trap it so they can deal with it. And of course, ADS space is nothing but the perfect mirror. If you really had to build something that would reflect gravitons, you'd have to build it out of space-time itself. And so this is just kind of a glorified version of putting the black hole in a box. Also, let's start by thinking about a black hole which is very small compared to the size of the ADS space. So small that it completely evaporates. All of its outgoing photons completely evaporates. And before the first photons get anywhere near the boundary. So there is some region here in the center of size of order LADS, where the geometry is basically flat space. And so we imagine a black hole which is so small that its lifetime is so short that this happens, and so it's going to be just like flat space. And in particular, a black hole of this mass will then not be stable. Black holes have a lot of entropy. Black holes have more entropy than ordinary matter of the same volume and mass. But if you consider the box a very big box, then the number of states of the ordinary matter grows. And so for a box of sufficient size, the thermodynamic state, the favored state, is not the black hole, but the gas. And in fact, there's a calculation which is worth doing. I'll do it first in 4 dimensions, which is, suppose I have a volume, so some radius here and some amount of energy m, and I want to compare the entropies of a black hole and a gas with the given m and r to see which has more states. So for the black hole, it's easy. S is just r squared over g. Oh, sorry. For the black. Sorry. So I want this to be a black hole size thing. So in particular, r is equal to 2 gm here. So the entropy is order r squared over g, which is again of order g m squared. So that's for the black hole. Now for the gas, the mass goes as t to the 4th times the volume, and the entropy goes as t cubed times the volume. And again, I'm leaving out numerical factors and things like numbers of species. And so if I solve for t in terms of m, oh gosh. Okay, I'm going to stand here while you all do this. Yeah. No, I know. Anyway, I'm going to look at my notes. I'm just going to waste time if I try to do it in real time here. This becomes mr to the 3/4, which becomes it becomes gm squared to the 3/4. And again, this is basically the area in Planck units, and so is this. So this calculation set, so I'll tell you I'll tell you what the answer is, and you can easily check it. It's that if I have a black hole, again, then its entropy is of order the area in Planck units. If I have a gas of the same mass and volume, its entropy is the order of area to the 3/4, so a power less than 1. And so the black hole has much larger entropy than, especially because we're comparing now E to the area versus E to the area to the 3/4 number of states. The black hole has vastly more states than the gas. But again, as we increase the volume available to the gas, then eventually the gas wins. And so I put the calculations in the notes. The notes are not yet on the web because I want to leave you with a homework problem. I don't want to give you the answer yet. So I'm going to try to do two things in 5 minutes. The first is so here's Schwarzschild radius, and so there are here is LADS. Here is LADS times n to the minus 2/17. So a number less than 1, and that number is derived in the notes. And if you ask what configuration has the greatest entropy in these three regimes, you get three things. Down here, for the lowest mass, so this is the mass parameterized by the Schwarzschild radius. For the lowest mass, again, the black hole evaporates, and we have a gas. For past this point, but before we get to LADS, we have a 10-dimensional black hole. That is, it's smaller than the ADS radius, so it's sitting in an essentially 10-dimensional flat space. And finally, when we get to larger than LADS, we have a 5-dimensional black hole. That is, it simply fills the S5, the 5 sphere, and it's just the 5-dimensional ADS black hole. So there are three phases, and again, these phases are where we specify the mass, and we increase, or the energy of the system, and we increase the energy. If you instead write down this in terms of temperature, I'm going to draw one more curve on this. Here's the temperature. It rises, then it falls again, and then it rises in these three phases. And so this phase is thermodynamically unstable. It has a negative specific heat. The derivative of the temperature with respect to the energy is negative. And so the true stable system as a function of temperature is given by the Maxwell distribution. So thermodynamically, that is, at fixed temperature rather than fixed mass, there are only two phases. There is this gas phase, and there is this black hole phase. When you plug in the numbers and translate it into gauge theory parameters, the gas phase has an entropy of order n to the 0 in gauge theory parameters, whereas the black hole has entropy order n squared. And this has all been on the bulk side, but this kind of phase transition is very familiar in gauge theory. It's a deconfinement transition. At low temperatures, the spectrum can be characterized as the spectrum of color singlets in the gauge theory, which knows nothing about the size of the gauge group. At sufficiently high temperature, the colored constituents deconfine, and you get instead a density of states and entropy, which is characterized by the number of colored constituents. And in fact, this phase transition is visible very nicely even in the weakly coupled gauge theory, but it's strongly believed to carry even to the strongly coupled gauge theory. So this is, again, one of the nice things where you see a nice correspondence between the expected physics in the gauge theory and the physics that you see in the bulk. Now, I saved myself 1 minute to give you a homework problem. And the homework problem is not really directly related to the black hole problem, but it's to kind of drive home a little bit of entropy, and it might come up again. It's really to review statistical mechanics. So I give you two vessels, each of which starts with a piece of ice at 0 Kelvin. Okay, they're sealed vessels. There's a discrete spectrum of states. I can get there. Yes, I can, because it's a finite system. So it's a discrete spectrum of states. I can do this. They do it with cold atoms now all the time. But the first one I'm going to put in contact with a huge bath at temperature 400 Kelvin, which is above the boiling point of water. This is system A. This is system B. And so it becomes steam eventually. And then I'll take the bath away. This one I'm going to heat up with a laser to the same energy density, so it too becomes steam. The difference between the two systems is, for system A, the density matrix is strongly mixed with that of the bath, and so the von Neumann entropy is large. SA equals big. Here I started with a definite quantum state, and I threw in energy, but using quanta in a definite state. And so here I'm in a pure state. I'm in a pure state. And S sub B is 0. So I have two vessels full of steam, one of which has an enormous von Neumann entropy, and one of which has 0 von Neumann entropy. And your homework problem is to figure out how, by ordinary quantum measurements, I give you these two vessels, you can tell me which is which. Okay. And you're not allowed to just say, I measure the density matrix, because that's not an ordinary quantum measurement. An ordinary quantum measurement is measuring basically eigenvalues, measuring a Hermitian operator, or equivalently acting with a projection operator. And by the way, okay, yeah. So your job. But I don't tell you exactly how I prepared the pure state, just that it is a pure state. If I told you how I prepared it, actually it would be easier. So here's your problem. How are you going to distinguish which of these situations we're in? Okay, I'm done. Yeah.
Can I rephrase?
Yes.
I can forget about the laser. The point is just you put it in some state of definite, pure state of the same energy density.
That's right. Yeah, that was the point.
If you really did it with the laser, it would be tangled with the radiation.
Well, I want it to be perfectly absorptive, so there's no. I should have said that. Yeah, I prepared a pure state, but I want to be very graphic about the pure state. Yeah. I'm doing this because with all of the story of entanglement entropy and density matrices, we sometimes forget how quantum mechanics works, and so this is partly a reminder of how quantum mechanics works. Yes.
We allowed 100 copies of it.
Okay, so there's two parts to the problem. In the first part, I give you just one of A and one of B. In the second part, I give you two of A and two of B. Yes. Yeah. Okay. Any questions about this or anything else? So next time, I think I probably have a few more words about ADS to say. Sorry this went up kind of fast, but it will all be in the notes. And I will post them. I won't make you sit. But then I'll go on to, where do we go from here? Yeah. Yes, Shanta.
So I have basic confusion about what.
Yes.
That is because supposing I start in the infinite past
Mm-hmm.
With a pure state.
Yes.
Okay. Now, a pure state has 0
Yes. Yeah.
quantum mechanics.
Yeah.
Now, this evolves according to quantum mechanics unitarily.
Yes.
Entropy stays 0.
Mhm.
Okay?
Yes.
Now, at some point, you say you have a black hole.
Yeah.
When you say you have a black hole, you are saying that this is entangled with something else. You are talking about a reduced density matrix,
Right.
which has entropy.
Right.
So at some point, you have gone from a pure state to the black hole state, and that means there is some extra quantum mechanical intervention,
Right.
which is like collapse of the wave function, which of course is well known is not a unitary process. So now you're trying to describe things, and you're creating a puzzle when there shouldn't be a puzzle.
So, so the puzzle. So, so if we just close, well, good. So if we just close our eyes to what happened in the middle, at the beginning we have a pure state. At the end we have, again, no black hole. We just have some radiation. And the most complete description we have of that radiation, the most fundamental description, is a density matrix. So something has happened, which is doesn't happen normally in quantum mechanics. I mean, now there's actually, if we once we understand the homework problem, we can actually think about measurements that would see that this has happened. But
That's
yeah.
notoriously an unsolved problem in quantum mechanics.
Not really. Measurement is.
I mean, you can.
You mean measurement?
Yeah.
I would say it's a solved unproblem. That is,
No,
well,
what I mean is
yeah.
that if you want unitary evolution,
Yeah.
whatever it gives you is unitary evolution, which means you have this multiplicity of universals, and that's unitary evolution.
Good. So, well, there is this larger question. The larger question is what is quantum gravity, but also, what is the right language for quantum mechanics in gravity? Is there a big Hilbert space? Does every observer have their own Hilbert space? Are observations connected with wave functions in the usual way? And I mean, this is a question that we have to answer. And I think what's clear from the last couple of years is that this paradox is forcing us to think about these questions again. But I wouldn't say it's not a problem. And in fact, again, let me start at the beginning of the next lecture. I will talk about this homework problem, and I will talk about your question in the same context. Yeah. Okay. So see you after the break. Okay.